Good morning. When I started preparing this, I didn't realize it's going to be at 8:30 a.m. So brace yourselves, this is going to be tight. Okay, quickly. My name is Rakhim. I teach computer programming. I live in Finland. That's my blog and Twitter. This is the company I work now at the moment. It just started, not much there. codeexpands.com. The plan. We want to talk about quantum computing and how it applies to cryptography. But to do it, we have to build the base a bit. So we're going to start with the computer and how to build a computer, and then move to cryptography using regular modern computers, and then learn a bit about quantum mechanics so that we are able to understand something about quantum cryptography and the ways quantum computers break modern cryptography. So, computer, made of bits, you know all that, could be 0 or 1. It's not a physical thing, it's just an idea. I can be a bit, so I can say this is me 0, this is me 1, and now I can encode something as long as we all accept this language. A light bulb can be a bit. Electricity could be a bit, like low voltage, high voltage. That's how your processors actually use bits. It could be physical, like in a laser compact disc. You see these nice colorful things. They are there because the surface of the disk is not actually flat. It's flat and has so little pits, and they don't directly correspond to zeros and ones, but they are technically like bits. So you can use something to encode something into bits as long as you all accept the rules. Now, when you have bits and then you combine them into logic gates, any programmer knows logic operators like AND, OR. Again, this is just an idea. And if you have, again, I can be an AND gate. Like, give me 2 bits, I'll give you the answer. You can implement them or an OR gate. You can implement them using something physical. You can probably train a dog to be a logic operator because, well, it's not much there to learn. Here's an AND bit implemented with dominoes. So this guy pushes 2 things, which means 1, 1, and the answer is also 1. Falling down means 1. But if he pushed only 1, left one or the right one, the answer would be 0 because 0 and 1 is 0. The way logic gates are implemented in modern computing is with transistors. Those on the left, they're about coin size big from about 50 years ago. And then you see they go smaller and smaller. And that's basically an electric switch. And your modern CPU has like billions of those. Why? Well, if you combine them in somewhat complex ways, like here, you can make math. Because if you combine gates like this, and you put some input bits, you get the sum of those bits. And that's the full adder. That's how it works in action. As long as you keep adding stuff, you can get more and more complex math. Because if you have addition, you have multiplication. And if you have multiplication, then you can have everything. Because multiplication is the key to everything. And here's, by the way, a nice sci-fi book I read recently. Highly recommend it. There are multiple cool ideas in this book. One of the ideas is there's this civilization. They don't have computers or electronics, but they do have a notion of computing. So they use soldiers to implement logic gates. Thousands and thousands of soldiers, and they have this rule that flag down means 0, flag up means 1, and then they arrange soldiers and they try to compute some hard mathematical problems. So if you have bits and you have logic gates, you have a computer. Now, this part is, of course, the most difficult. And I'm skipping it because we only have so much time, and this is similar to this. It's like you do something and then magically you have the answer. But if you're interested in those hard bits, how do you go from bits to modern computers, then I also highly recommend those 2 books by the same author. One of them on the left goes from light bulbs to modern computers, and the second one talks about the scientific paper by Alan Turing that started this whole thing. All right. So we assume we know how computers work. That's how they basically work. You are here. We are now ready to talk about cryptography. As you know, cryptography is a way to make information secret, to hide something so that only specific people can read your messages. So one of the simplest and most obvious ways to encrypt a message is to just shift it within the alphabet. We've done it as kids probably, and Romans did it thousands of years ago. And if you just take some, say, English text and shift it by some number like 3, you get this. And if you're not from Hungary, this is not Hungarian, although... Sorry, I had to do it. So Romans used it about 2,000 years ago, and I guess it worked for them because they looked like that and their enemies looked like that. So not much to hide there. But today, that won't work. It's so easy to crack it. You can just guess. You can look at, and the worst case scenario, you just try all the combinations. And in English, there are 25 different options. So this is the idea behind the simplest symmetric encryption. And up to about the 70s, that's all we had. This is the top of the symmetric encryption machines the Nazi used in the World War II. It's much more complex than the simple shift, because for a single letter, they used different combinations every time, and they changed every day and then every month. But it's still something that a first-year computer science student can crack in about 50 lines of code today. That's symmetric encryption, where you use the same key to encrypt and decrypt. And now your problem lays in this communication of the key, because as long as someone has the key, they can encrypt your message. So this is not perfect. This is why from about 70s, we have a much better idea of asymmetric encryption. And the idea there is, let's say this on the left is me, on the right that's my sister. As you can see, we are related. I don't have a key. She has both the key and the lock. And the lock is public. She gives it to everybody. When I want to send her a private message, I take her lock and I encrypt my message with her lock and give it to her. Only she can unlock it, because only she has the key. She never shares the key. That's the basic idea. So it could be done with locks, but we only have computers that can only do math, nothing else. So how do we do it with math? Well, we need something that is mathematically easy to kind of lock one way, but hard to unlock if you don't have the key. And one of the things that works in math like that, and it's called the one-way function in math, is multiplying large prime numbers. If you just pick 2 prime numbers, you multiply them, it's easy. You can do it on your computer even if the numbers are really, really big. But if you have that number n, it's really hard to find what prime numbers were used to produce it. So how to apply this idea to encrypt messages? Oversimplification again, but this is how the RSA works basically. You pick 2 prime numbers. Let's pick really small ones, 2 and 7. You multiply them. You then find a special value called phi of n. There's a whole bunch of number theory in it. We won't cover it, but trust the system. This is the formula you use and you get 6. And now the fun part. You pick a number E, which is your encryption key. And again, you have some constraints. You don't see it, but there's math, number theory and math there. But you have a few choices when you have large prime numbers. So I pick 5 within those constraints. And then I also pick D, which will be my decryption key, the secret key. Again, I have some rules to pick it, but I have some choices, and I choose 11. Now we have the kit. We have the public keys, and we have the private key. So my sister generated all that. I want to send her a private message. So I take her public stuff, the 5 and 14, and now let's say I want to send her a simple message, C, letter C. I convert it to a number any way I want, maybe UTF, like a Unicode or whatever. I convert it to number 3 because C is the 3rd letter of the alphabet. And then I take 3, raise it to the power of that E, 5, and see the result mod 14. And mod 14 is the remainder after integer division. So we have 243, we divide it by 14, we get the remainder 3. Oh, sorry, 5. 5 is the secret message. This is the thing that I'm going to send her. And she can see now she has the private key and she has the encrypted message. She does the same thing, but with the private key. So she raises it to 11. She does mod 14. She gets 3. And that's how it works, basically. There are more layers to this, but that's the idea behind much of modern cryptography. So you see, the problem here is it is hard to guess those numbers, and it is hard to find them. With large enough prime numbers, it will take billions of years on a regular computer to just find those prime factors, because basically the only way you have is to try all of them. All right. We have the idea behind computers, and we have some ideas about cryptography. Now, to talk about quantum computers and quantum cryptography, we need to dive just a bit into quantum mechanics. So remember in chemistry classes in high school, we talked about those covalent bonds. Like you have H2, which is 2 hydrogen nucleus connected, like sharing an electron. And I could never understand, like, sharing an electron, is it like going around 2 nucleus at the same time? Is it like running around? Because I have this idea, and many of us do. This is the atom, right? It has the nucleus, and it has electrons, like planets, running around them. And that picture is nice. It's easy to understand, but it's wrong, because electrons actually are not those balls that could be anywhere. The idea of asking, where is this electron at the moment, does not make sense. Because if you don't ask that question, if you don't look at the atom, it's not anywhere. It's not in any particular place. So it's not like that electron is running around the nucleus. It's a probability around that nucleus. And it has some probability of being here and being here. So it's a cloud of somethingness. And when they say 2 hydrogen nuclei sharing an electron, that means the electron is at both places at the same time. It's with that nucleus and with that at the same time. It does make sense. It shouldn't, because quantum physics is like that. It's counterintuitive. We hate it because it doesn't fit the way we think about the world naturally. So, for the longest time, scientists were asking a question, what is light? You know this probably from physics in high school. Is it a wave? Is it a particle? And the problem with that question is, if you are into waves, you can produce experiments that will prove it's a wave. If you are into particles, you can produce experiments to prove it's a particle. So it's hard to guess, it's hard to find out. And one of the ways to think about it is, well, if it's a wave, then it should behave like a wave. So if you have like a wave of water and you put 2 slits in front of the waves, then on the other side, you should see this interference pattern. Like, here's the screenshot from a video on YouTube where a guy pushes 2 balls onto the flat pond of water and produces 2 sources of waves. And those waves collide into one another, and they produce these flat pieces where waves, like high point of wave goes with a low point, and they cancel each other. And at some points, they amplify each other. This is why you have the interference pattern. But if particles are shot through the same double slits, then you should see just 2 lines, right? They go through left one or through the right one, like it. I'll switch to this one. Okay. So the problem with this is, if you look at particles like photons or electrons like that, then you do an experiment and you shoot electrons or photons through double slits, you still get an interference pattern, as if it's a wave. And okay, well, that proves it. It's a wave then. But they think, okay, maybe it's not a wave, but there's still like little balls of things that collide with each other and produce this interference pattern. So let's shoot them one by one, just one at a time. And if you do it, you still get the interference pattern. Like one thing, it goes through something like the left slit or the right slit, and then it lands on that side as if it was part of a wave. It doesn't make sense. And the only good explanation to that is it's going through both slits at the same time. you shoot one electron, it goes through both things at the same time with some probability and then collides with each other on the other side and produces the interference pattern. But if you put detectors on the slit and you want to see, is it going through the left one or is it going through the right one, you'll see the answer. Like, this one went through the left one. But you won't see the interference pattern anymore. On the other side, you'll see two lines, as if those were particles. So the fact of observing the answer collapses the answer to one thing. And it's not like our minds controlling the universe by observing it. It's because at this point, observing means interacting. You cannot observe a photon without touching it, like kicking it. And by doing it, you collapse it to one possible scenario, which is left or right. So, things on this scale, like photons, electrons, even small atoms, behave like that. And they could be in, for example, two states at the same time. They could be at two states at separate times. So, with things like photons on the right side, there is a property called spin, which is a bit harder to get at this point, but we can just think of it as a photon looking up or looking down. So it could be in one of those states, and you can apply some energy and move it from one state to another state, which means you can use them to create bits, just like you use light bulbs or electricity. And at this point, this is no better than any regular computer. You still have bits, you still have two states, distinct, discrete states. But those quantum objects, as I said, they can also be in both states at the same time with some probability. So we could have an electron that looks left. So it's kind of somewhere between 0 and 1 with 50% probability. And that's what they call a qubit. It could also be like this way. And technically, you can have many, many more possibilities and technically infinite number of different states between 0 and 1. So if you have computers with bits and logic gates, then quantum computers are quantum bits with quantum gates, the gates that operate on those qubits. And again, this is the long part which is the most difficult. Now, if you Google about quantum computing and look at popular articles or lectures or stuff like that, there are a few levels of the way they describe it. And one of the first levels is some journalists might say, well, quantum computers have more than ones and zeros. Our regular boring computers only have 2 bits, 0 and 1. And these powerful quantum computers have more than 0 and 1. That makes them really, really fast, which is, again, not really true. We could have more bits than 0 and 1. There's not like a physical limitation to that. And there are actual computers with trinary systems where they have 0, 1, and 3, or 0, 1, and 2. And it's not that gives us power. 2 bits is enough for all the power we need. Another level they might describe it is, well, the bit can be 0 and 1 at the same time. This means this computer is infinitely parallel. Like this quantum computer does something that a classical computer does, but it does it in infinite many states at the same time. So it's like a super parallel computer, which is technically true, but effectively isn't. Because if you look at this and you think a quantum computer is just a bunch of classical computers working at the same time, it sounds really good, but the problem is they do, but at some point you want to get the answer out of those. You only get one at random. So it's not really, it's not helpful to think about quantum computers as computers, classical computers that work in parallel. It's like a superposition of multiple classical computers, just like a photon on an electron could be in superposition of different states. So if you are looking for factors of n, like those prime numbers, then your machine is in different states of looking at different numbers at the same time. But then you want to see the answer, and it gives you the answer. Like it says, this number is not a factor. Well, that's not helpful. I could have done that with a classical computer at random. Just pick random numbers and see if there are factors or not. So it's kind of similar to this, to a gaming die. When it's in the air, it's in like superposition of different states. But it's not helpful because you want to see the answer and you put it on the table and you only have one answer. It collapses to that one answer. So you keep going and you say, okay, this is also not a factor. And if you're lucky, then at some point you get, okay, this is a factor. Again, you could have done it with a classical computer at the same speed. So this particular property of quantum computers, that's not enough to solve that particular problem of finding prime factors. But they do find prime factors by changing the problem, by taking advantage of these weird quantum properties. Because if you switch from the idea of finding prime factors to a problem of finding a period of a function, which is again provable by means of number theory, that you can kind of rearrange the problem into finding a period of some function and then at some point get the prime factors, then your answers are still random, but then less random than that. They are less random than a perfect die. They are more likely to land on a particular value, which is the correct answer. So you might repeat the same thing multiple times, and then you see the answer is X is more likely to be there. It's statistically more likely. And it's like a gaming die which is crooked, like it's not fair. Maybe it's heavier on one point. If you throw it multiple times, it's more likely to land on one side. And this is the idea behind many algorithms in quantum computing. This particular one is called Shor's algorithm. And the idea with other algorithms as well is that you make the problem so that you play with it so that it's more likely to not give you a completely random answer, but more likely to give you a correct answer. And with repetition, with enough tries, you just look at the statistics, and this top answer is probably the correct one. This lower one is probably the wrong one. So this is how roughly you get about solving problems in cryptography with a quantum computer. Now, the idea there is you have a problem designed for a classical computer, and the problem of finding prime factors is really, really hard on a classical computer. It could be somewhat easy on a quantum computer. We're not there yet. Well, the problem with quantum computers is you need something to have those bits. You need those atoms or electrons or photons, and it's really hard to control them, because if you put them in some state, then basically any fart can change them. Anything like a smallest interaction with a particle flight or temperature can change them. So it's really hard to make this computer a stable computer. This is why those fancy quantum computers are so big. Most of that space is, it's basically a fridge that you want your quantum computer to be at about absolute zero, so that no jiggling, no temperature affects it. But at some point we will get there probably. Shor's algorithm was implemented was like written before quantum computers existed, and then it was implemented with one of the first quantum computers, and it produces the answer that 7 is a factor of 21, which is good. We're getting there. But we need now to scale it to like billions and billions. But this could be a race with no end. Like we could create new algorithms that are harder and harder to solve, and then maybe come up with more quantum algorithms to actually solve them. So what can we do to guarantee that we can create some cryptography that is unbreakable by even a quantum computer? And this is the area of quantum cryptography. Actually using these weird quantum properties to create new algorithms based on quantum properties to encode messages. And we're going to jump right into it again. This is an algorithm called BB24. And we are back to the land of symmetric keys. So the idea is we want to share the same key and use it for encryption and decryption. But now we're going to use it quantum way. So those balls, again, are, let's say, photons. And it can look up, it can look down, it can be in one of those positions, and then left and right. And you have detectors to detect what position is it in. If you use the correct detector, like if you have up or down photon and you use the vertical detector, you get the correct answer. You get 0 up, 1 down. But you also have a horizontal detector. And if you use the horizontal detector on the vertical photon, you get a random answer, 0 or 1. So you basically have like the correct detectors for a photon and the incorrect detector for a photon. So my sister generates a series of random bits. It should be big enough, but in this example, it's small. Just at random. She then picks random detectors for each bit. Again, completely random. And based on those, she produces qubits. She produces photons of the correct orientation. So that if I were to know the detectors, she gave me the photons, I could produce the same bits. But she doesn't tell me the configuration of the detectors. She only gives me the qubits. So I get those photons in some configuration, and that's it. This is our first point of communication. And this communication is done on a quantum channel, on a channel that is capable of sending qubits. In this example, we are using photons, so we could use something like a fiber optic cable that is capable of basically moving a photon from one point to another without changing its orientation, its state. So this is still communication, and this is still like some cable lying around. Someone could listen to it, right? So let's say some evil person listens to the communication. That's my go-to evil person in all the presentations I use. The problem there is it's a quantum communication with quantum bits. And if Hitler listens and tries to see what qubits are there, he needs to use detectors. But he doesn't know what detector to use. If he uses the wrong detector for a qubit, it will flip to either 0 or 1 at random. By doing it, he might change the qubit. So when I receive the message after Hitler listens to it, I might get a different message. And with the long enough messages, I am guaranteed to get the incorrect message. And you'll see how this works in our favor. So let's say I get the message. I then also pick detectors at random because I don't know the correct configuration of detectors. So I just pick them at random and I produce some bits by applying them to the photons. If you think about it, you can see that statistically I will get 75% right because 50% of the detectors I will choose correctly, and out of those 50 incorrect choices, I will get 50% at random correctly. So I'll get 75% of bits correctly. Then I just call my sister on a regular unsecured line like a phone, and we just compare detectors. We don't talk about bits, we don't talk about photons. I say, for the first position, I chose that detector, and she says, me too. So I see, okay, then my bit should be correct. On the second, I chose this detector, and she says, no, I chose that detector. And I say, okay, this bit is incorrect then. I chose the wrong detector. So I just discard the wrong bits, comparing them. And again, at this point, Hitler might be listening too, because it's now just a regular phone line. So he listens and he says, okay, he now knows the configuration of detectors that we used. But he doesn't have the photons in the same state. Because if he had, then I would have gotten the wrong message. So after doing this, we just discard the wrong bits, and now we have the shared key. And it's all about statistics, because with message small enough like this, Hitler could be lucky. But we need to produce big messages, and then we are guaranteed statistically to be safe. And there are also ways to detect if the message was listened to, because we can also detect changes in the state of the qubits. This was really fast. I'm not sure if this is enough. It's a really quick overview. There are resources that you can get into to learn about. This is fascinating. And this was a theory for a few years, and then they actually implemented, and all over the world in multiple places they could create a secure channel by doing this quantum encryption. And actually, if you drive from here for about 2.5 hours to the east, they did one of the first demos in Vienna where they created a secure channel, multiple links, and it works. It's amazing. So even though quantum physics is this weird, unpredictable randomness, which doesn't make sense to us because we want things to be not random. We want things to make perfect sense. We want to predict outcomes. It turns out we can use this in our advantage. So this fundamental property of the universe of not being sure about itself can be used, for example, in secure communication. So if you want to learn more about this, there are a few resources that I recommend. There's an interactive essay, and there's this blog by a quantum scientist. And he also wrote a book called Quantum Computing Since Democritus. And there are a few channels on YouTube. I particularly recommend this Frame of Essence channel, which describes both quantum computers, qubits, and quantum cryptography using this algorithm that I described and some other algorithms. Those links will be on my website at this address. Feel free to ask me questions or anything. I'm not a specialist in this area at all. I'm just really curious about it. I think it's quite amazing. And thank you.